The following is a videotape module from the learning system Seymour Papert on Logo. The tape series has two parts. The first, New Mindstorms, focuses on the process and the principles of learning. The second, Logo Hurdles, focuses on specific technical aspects of Logo. This is Hurdles tape number 3. Images of recursion. Like the other Hurdles modules, it is intended for use with on-Logo study guides and computer diskettes.
What is that, a Polaroid?
Jack and Jill, what are you doing?
I'm taking a picture of her, taking a picture of me, taking a picture of her, taking a picture of me, taking a picture of her, taking a picture of me.
Stop it. Why don't you just take the picture?
Because I'm not finished. I've got to say what I'm going to say before I can do it. I'm taking a picture of her, taking a picture of me, taking a picture of her, taking a picture of me, taking a picture of her, taking a picture of me, taking a picture of her, taking a picture of me.
The story of Jack and Jill is, of course, a joke, but it's a serious joke, almost a philosophical one. In this tape, we'll see how this joke is quite closely related to an idea of great power for solving problems and for understanding the world around us, an idea called recursion. We'll be studying recursion primarily as a technique for Logo programming, but through Logo programs, I think you'll get some deeper insights into the use of recursion beyond the computer. The tape's divided into 3 parts. 3 ways of approaching recursion, which we've kept as separate as possible to allow people with different tastes and styles to choose the one they like best. So spin through the tape quickly and then choose the one you want to focus on. Come back to the others later. We see from Jack and Jill that there is a lot about recursion that's paradoxical. And among the paradoxes, one is related to learning. Some concepts are hard to learn because they are so complex. To get at them, we have to penetrate successive layers, veils of complexity that stand between us and the concept we want to grasp. If recursion is difficult at all, it's difficult because it's so simple. I like to think of learning it as drawing aside a veil, not of complexity, but a veil of simplicity. I'm fond of approaching recursion with children in an extremely simple way. In fact, through a joke not unrelated to what we saw Jack and Jill doing to one another. These children are playing a game which I've played with many groups. When I say wow, that's the name of the procedure. When you hear wow, you put your hand up and you put it down. Let's try that. Wow. Wow. Okay, now we're going to change it. When you hear wow, you put your hand up, you pull it down, and you say wow. Let's have one person start. Who would like to do it? Okay, you do it. Wow.
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 Let's try somewhere else. You do it. This. Wow.
Wow.
Hey, when I said wow to her, why didn't you put your hand up? Let's try again. Whenever you hear the word wow,
Okay.
you put your hand up, you put it down, and you say wow.
All right.
Wow.
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 Well, what are you waiting for? What do you think's happening?
I'm supposed to do it again.
Why?
Because I said wow.
Okay. Let's try again. Wow.
Wow. Wow. Wow. Wow.
Of course, one can't get a computer to put up its hand, nor can it hear its own voice. But I think you'll agree that the program I'm going to show you works by the same kind of process as these children met in their people procedure called WOW. We use it here to make forever programs, ones that go on and on and on without stopping. Look at this one. When this procedure is run by this instruction, the procedure's first action is to note that dot side is 50. So that forward dot side will become forward 50, and the turtle's action will be forward 50, right 90. The procedure's next action is square 50, which will start the cycle over again. Side is, of course, still 50. The turtle does once more forward 50, right 90. And you might be asking yourself, why do we need such a fancy thing as recursion to draw a square? Surely repeat would be good enough. Indeed, repeat would be adequate if our interest were in the product. But if our interest is in exploration, recursion allows us to make such changes as this. I replaced square dot side by square dot side plus 10, and this small modification will give rise to the most surprising and interesting mathematical results. Side is now 60, forward 60, right 90 is going to bring the turtle down below that line. We will now do square 70. Side will be 70. Forward 70, right 90. You guessed it. Square 80. Side will now become 80. Forward 80, right 90. And where's it going to lead? A full screen version shows the pattern. Forward a distance, right 90, increase the distance, repeat. We got this quite interesting result by making a small change to the procedure for square. Let's follow that rule. Make a small change to this. Instead of 90 as the angle, let's try 93. Notice how we get this effect of twisted squares. Notice that curved line that appears, an emergent phenomenon. Quite interesting. So let's try to do the same thing with triangles. First, straight triangles using 120. Same process. 123, forward a distance, right 123, increase the distance, repeat. A very interesting result. And since 90 and 120 gave something interesting, let's try 180. It's sort of in the same family. But the result, as a product anyway, doesn't look so interesting. Think about the process, though. Maybe if you rotated that as it went up and down, for example, by trying 177 instead of 180, look how it turns as it goes backwards and forwards. I see this as a result that's interesting in lots of ways, visually, mathematically, and as an example of what happens when you follow a powerful heuristic. I think it's pretty enough to try again without being cluttered by all that text on the screen. It's worth thinking about, too. In all these spirals, there's a common pattern. You draw a line, you turn, maybe 90, maybe 93, some other angle. We've been exploring what happens when you vary the angle. But you could vary something else. Instead of a line, you could have another figure. In fact, in the example I have on this other computer, the figure is a triangle. What's going on in this program is draw the triangle, turn, draw a slightly larger triangle, turn, draw a slightly larger triangle. What comes out looks like a seashell. I chose spirals as an entry point to recursion because such simple, such small changes can so often produce interesting, surprising, and beautiful results. The possibilities are endless, like recursion. So why don't you go and try some yourselves and come back when you're ready to move on. We began part 1 watching children enact a procedure, a very simple one, to wow, hands up, hands down, wow. We'll begin part 2 revisiting the same children as they enact a rather more complex procedure, which I have written on this piece of paper. This is a procedure that draws a spiral and does some other things as well. Without this last line I'm covering with my fingers, this is a perfectly familiar spiral procedure. Spiral does a forward, does a right, and runs spiral with side plus 10 as input. That's what makes it spiral. But what about that? What does print wow have to do with a spiral? What it has to do with is the difference between the intention of part 1 and part 2. In part 1, we tried to make our procedures simple in order to put spirals on the screen so we could study them. Here, our intention is to understand what goes on inside the procedures, particularly to make mental models. And to make mental models, we'll sometimes, a little perversely, put tricky features into the procedures in order to check out how well we think about them.
Okay, let's get started. Laura, I want you to be the turtle at home. We'll need more actors. I want all of you to stand in line over here and wait for your call. Laura, here's your script, Spiral 10.
My input is 10. 10 is not more than 50, so I don't stop. Forward 10, right 90. 10 plus 10 is 20. Spiral 20.
My input is less than 50, so I don't stop. Forward 20, right 90. 20 plus 10 is 30. Spiral 30.
My input is 30, and 30 is less than 50, so I don't stop. Forward 30, right 90. 30 plus 10, spiral 40.
My input is 40 is less than 50, so I keep going. Forward 40. Right 90. 10 plus 40 is 50. Spiral 50. My input is 50. It is not larger than 50, so I keep going. Forward 50. 10, 20, 30, 40, 50. Right 90.
Put yourself in the position of one of these children. Maybe the second to last with input 50. Dot side is 50. It's not greater than 50, although it's pretty close. You don't stop. Forward, you do it. You ask the turtle to do it. Doesn't matter how you think about that. It's all very straightforward. This is where there's a tricky point. You need to find a subordinate. You yell, spiral! Somebody comes and you give the input. 50 plus 10 is 60. Meantime, you go to sleep. You know when you wake up, this is where you'll be and you'll continue. Meantime, your subordinate is the one who's going to stop. When your subordinate stops, you're woken up. You're told, wake up, my job is done. And at this point, you go ahead here, you print wow. So wow is going to be printed many times. And then you wake up, the one who appointed you to do spiral. What I'd like you to note particularly is the two-way movement. Somebody appointed you, your boss. You appointed a subordinate. The subordinate woke you up. You woke up your boss. Note the two-way movement, which is about to turn around in the game.
50 plus 10 is 60. Spiral 60. My input is 60. 60 is more than 50, so I stop. Wake up, I'm finished. I'm not finished. Print wow. End. Wake up, I'm finished. Print wow.
Notice the two-way action. The action rolls out as they do the forwards and rights. As they do the wows, it's rolling back.
Wow. In.
All recursive procedures have this two-way action, though often there is no visible effect of the roll-back part.
And wake up, I'm finished.
Print wow.
I bring this segment to a close by suggesting an exercise which may help you appropriate acting out as a technique for your own mental modeling. Watch the performance again, but this time imagine that a change has been made. Print quote wow has been replaced by print dots distance. What will the children put on the chalkboard? Test your prediction by writing the procedure and running it. Try some other modifications. Write a procedure that will do this. The turtle draws the spiral and then eats it back again. I'd like you to achieve this by replacing print quote wow by something else and leaving the rest of the procedure unchanged. Imagine what would happen if you left out the stop rule. Think, as you imagine this, about the two children taking photographs, each taking a photograph of the other. One last piece of advice. End such a session as this with a brief discussion focused on a few salient points, just as I'm trying to do with you now. And just as in the next segment, you will see us doing with the children you've just been watching. One of the things that's fun, in fact funny, about recursion is that you solve a problem by getting somebody else to do most of the work. I call it passing the buck. You see this very clearly in an informal interview with two of the participants.
Laura, that must have been a lot of work for you to draw this spiral.
No, actually, I just did this line right here. Alex did the rest.
Was it a lot of work for you?
No, because I just did this line. I guess Matt must have done the rest.
The technique of passing the buck has a lot of applications. For example, someone wants me to add up some numbers. Here's a list of numbers. Looks like a lot of work, but I'm not going to do it. I'm going to take the first of the list and I'm going to hand on the rest. Add up those numbers for me, please. All I need to know is that I've kept 2, and when I get the sum of the rest, I just have to add that onto 2. There it comes, 37. 2 plus 37 is 39. Your answer is 39. That's my output. We've seen the technique in the geometry of spirals. We've seen it in dealing with numbers. I'm going to make it really concrete now by looking at it in a problem involving sorting children's building blocks. It's really the same thing, however unsophisticated it seems. I've recruited some people to help me find the largest of the set of 5 blocks. Of course, I can see which is the largest. This is a toy problem we're doing for the principal. Issues of method would be the same if there were 5,000. One method would be to compare them 2 by 2. The recursive method is very different. Look at it like this. I have a problem. Find the largest of a set of 5. I reduce the problem by taking one out. And it doesn't matter which. It could be a random choice. It doesn't matter how I choose it. I have 4 blocks which I pass on, and so someone else has the simpler problem of finding the larger of a set of 4 blocks, and they're the largest of a set of 3 blocks, and the largest of a set of 2 blocks, and he has no problem at all. He gives what he got. Now each player makes one comparison and passes back the larger. Notice the two-way movement typical of recursion. Eventually, something comes back to me. I passed off a set, I got back a block. I make one comparison. This block, which I know to be the largest of the set of 4 that I passed off, and so the larger of these 2 must be the largest of the lot. This is it, the largest of the 5 blocks. The 2 activities we've just seen, adding up a list of numbers and finding the smallest stick, are members of a very important family of tasks, of algorithms, that come up over and over again in mathematics, in science, in linguistics, in play, and in programming. In Logo, we think of them as recursive reporters. What they have in common is this. They take a list of numbers, list of sticks, and from this, they make a new Logo object which they give back to you. They have an output. That's what makes them reporters. I'm going to dig a little more deeply into this family of tasks, into how recursive reporters work, by programming a particular case of which I happen to be rather fond. I want to make a Logo version of the procedure I used to add up those numbers, or rather to avoid adding up those numbers, which I did by passing the buck. A first golden rule in designing a procedure like this is exercise your options. And here I can do that by at least choosing the language. I call the procedure add up, and I call its input numbers, so I can read the whole thing as add up the numbers, or add up of the numbers. A next golden rule is to put down whatever bits and pieces of information you have. This is a reporter. It's bound to have an output. The output is bound to be the sum of something. We'll come back to what it might be. And it has end. All Logo procedures do. Not much? Yes, it is. It's a skeleton that will help ground our thinking. And I've left holes to fill in the missing parts. Output sum of what? Remember concretely, and that's another golden rule, the situation most like this. When I was adding up the numbers on the paper list, I kept the first of the numbers. And then I said to somebody else, add up, and gave but first of the numbers, what was left when I tore off the first. And so just remembering that concrete situation guides us in making the core part of this Logo procedure. Think concretely now of the process of playing it out. For example, of the spiral game. Each actor passes the buck to the next. One add up says, add up this for me. And that one says, add this one for me. That's got to stop somewhere. There has to be a part of the procedure. That's what this hole is for, where the buck stops. I don't know what it is yet. So I put down vaguely what I know about it. It's going to be if something or another, well, an easy case. Do something. Now we can focus bit by bit. If what? Think of the block situation. The easy case was when there was one block left. If one of numbers left, what happened? Well, give what you got. There's no problem there. Adding up one number isn't a problem. What is a problem is that this isn't yet Logo, but that's not much of a problem. If one of numbers left, we can translate into if one equals count of numbers, and that is Logo, and give what you got, give turns into output, first of numbers. When there's only one number in the list, first of the numbers is it. So that's our procedure. And one last step remains, another golden rule. I'm going to label the 2 parts. This part is called pass the buck. That is called the buck stops here. I'm setting up a private language, something you should do in any problem. A private language for the micro world of the problem that I use not only to talk to others, but to talk to myself in thinking about the problem. What you see on the screen is the output of a visualization procedure which I'll use to follow the way add up works. You'll see this run in a moment, but please don't try and follow the details. Get the general gestalt. Then go to the diskette. Run this procedure which you'll find there, focus on the details, and then come back to review the tape afterwards. This procedure is a little bit like a simulation of the children simulating the way a procedure works. It's going to run a series of actors which will carry out add up and add up and add up. Let's see how it goes. We begin with the logo instruction. Print add up 3, 4, 5. And of course this has to print 12, but let's look at the process. The color coding you'll pick up. Green means the active procedure, blue means its input. Running this procedure requires an actor, and the copy of the procedure in gold will always represent an actor carrying it out. This actor gets the input 3, 4, 5, and dots numbers will be replaced line by line by 3, 4, 5 as we need it. There's the first line. If 1 is equal to count 3, 4, 5, which of course it isn't, and so if is going to get false, and this isn't going to happen, the part we called the buck stops is not going to be operative here. The work will be done by the passing the buck section. Output sum of what? First 3, 4, 5 is just 3, and here is the important part. Add up, but first 3, 4, 5, add up 4, 5, add up, and a new actor appears. This one will get as its input 4, 5. Notice the problem simplifying as the list gets smaller. But it's not at the end yet. Count 4, 5 is 2, so if once more will get false, this won't operate, and we'll move to the pass the buck section. Sum of what? First 4, 5 is, of course, 4, and then finally add up, but first 4, 5 is add up 5. If this procedure had any sense, it would realize that there's no problem there. But it's dumb, and so it calls another add up. Add up and tells it 5 is the input. This time, 1 will be count of numbers. Count of a list with one thing in it is 1. So 1 equals 1, and if gets input true, we will see output first of what? First of this list is just 5, and now 5 will be passed back. The trail of green shows where information was requested. This 5 was requested there, and it's passed back to there. This sum now has its 2 inputs, 4 and 5. Can add them together to get 9. It's now ready to report to its boss, the previous actor. 9 will go back there. Add up 4, 5, of course, is 9. This sum gets 3, 9 as inputs. That's 12. Aren't they smart? Output 12 goes up there, and prints 12. That is the product we expected. This module was called Images of Recursion, but in fact turned out to be an essay on solving problems. There's no conflict. In fact, for me, recursion and logo and computers are all interesting mainly because they provide us with such rich areas to explore in search of techniques and skills and images for solving problems of every kind.